Yeah. Okay. So it's the one but last. Come on. Session of this course, and I would again continue a little bit where we left off last time. So we calculated optical properties for particles, for dipoles, etc. And now we're interested in how we can use these properties in to describe light propagation, basically in bulk tissue. That of course is scattering dominated, so I'm not entirely taking it out of the title, but let's do it. So first, I want to do a quick lightning round, because these are the terms that will be that will come along a lot today. So can you briefly shoot me some answers to these questions? We don't have to take too long about this.
All right, I guess I'll start. Scattering efficiency is the ratio of scattered power relative to incident power.
Exactly. And then the scattering coefficient, scattering cross-section first, and then scattering coefficient next. Someone else maybe?
Yeah, so the cross-section is the scattering efficiency multiplied with the geometrical surface.
Yeah, that's correct. And do you know the units?
I would say squared meters, or yeah.
Yeah, it's an area. So the efficiency is dimensionless. That is a ratio of powers, and if you multiply that then with the geometrical cross section, you get an area. That's correct. The scattering coefficient. How did we arrive at that?
Scattering coefficient is either the density of the particle multiplied with the scattering surface, or a summation of the scattering area divided by the volume.
Yeah. So the formal definition is it's the density of scattering cross section. So basically you add up all the scattering cross sections, the total scattering cross section within a volume, and then you calculate the volume average. Yeah, that's correct.
Sounds a bit odd, right? You have a density of surface areas.
Yeah, so if the particles are all the same, then you can use the density, and then the scattering cross section is just one number if all the particles are the same. If the particles would be different, then you would just have to add them one by one, or with the respective densities for that particle size, something like that. Yeah. The unit of the scattering coefficient.
So that's per meter.
Yeah, that's per meter. We'll see that one a couple of times later. So that then can you give me a little bit of a formal definition of the phase function?
All right. So the phase function is it's based on the redistribution function, and then specifically the real valued redistribution function. It's small s squared.
Mm-hmm.
The phase function here, you divide the redistribution function by the scattering cross section and k squared to normalize this. Yeah. So the phase function is only left containing angular redistribution.
Yeah, only the angular redistribution, and the word that I was actually looking for, you also mentioned normalized. So it is a normalized function. If you integrate it over solid angle, so over 4 pi solid angle, then the answer is 1. That is all right, and then the scattering anisotropy, symbol G.
It gives you a measure of how much light scatters in the forward direction, right?
Yeah, correct. It is the projection of scattered light along the incident direction. So basically, it measures them the fraction of light that retains direction. Do you also know how to calculate it? So let's say you know the phase function.
Yeah, it's an integral over the phase function multiplied by cosine theta and integrated over solid angle.
Exactly. It's the average cosine of the scattering angle. So you multiply the phase function with cosine theta and then perform the integral. All right. Well, but basically question 5 and 6. So 5, I'm not gonna insult you by asking what the probability density function is. But do you know what the commutative distribution function is? So let's say we have a probability density function. Do you then remember what the commutative distribution function was?
Yeah, I have it in my notes. That probability that a random variable takes a value less or equal to that a certain value.
Yeah, exactly. That it falls. So the probability density function basically describes the probability in a very small interval around some value, and the commutative distribution is then the probability up to that value, as you say. So from some lower boundary to up to that value. Yeah, that's true. And then the last question 7, that is basically a little bit rephrased question as question 4. How do you calculate the expected value of a random variable?
It's an integration with x times the PDF, I think.
Yeah. So if you have a probability distribution, probability density function of some variable x, then to calculate the expectation value of x, you multiply x with this with this distribution, and you integrate it out. So you basically calculate the weighted average of the variable, and that's exactly the same thing that you do when you calculate the scattering anisotropy. You're calculating the expectation value or the expected value of cosine theta by multiplying it with the appropriate phase function. All right. So as you gathered from the title and from these questions, I want to talk a little bit further about probabilities and probabilistic methods to describe light propagation. I'm going to use the same assumptions as last week. So the scatterers are not waves or no electromagnetic wave description. It is just scatterers are particles, photons are particles, and they bounce off each other. So it is just one big game of billiards. Now, if you define a medium in such a way, so particles that are somewhere in the medium, and then photons that bounce off these particles, then you can define photon paths, like some kind of trajectory, like in the cartoon over here, some kind of trajectory through the medium where it enters here. Then it propagates to scatterer number 1. There it is scattered. Propagates to number 2. Where it is scattered again to 3, to 4, etc., etc. So this photon path is now a series of propagation steps where nothing happens. So just movement, and then followed by collision with the scatterer where it is redirected, and then etc., 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 until the photon I don't know, escapes from the medium, or it is absorbed, or something else happens. That is the basic picture. So the questions that you can ask them, probabilistic questions, is what is actually the likelihood of a given photon path? The one that I drew here, how likely is it that this one actually occurs? You could ask if you look closely, you see that the paths between the collisions are some are longer than others. So what is the distribution of the path lengths between these collisions? What is the likelihood that an absorption event takes place somewhere along this path, etc. These kind of questions. But before we go into that, I just want to briefly recap these probabilities again. So we already discussed the commutative distribution function very shortly, but I want to introduce a couple of more things. Probably you know all this already, but just for completeness. So first, let's look at a random variable x and its probability density function p of x. So for the probability density function, I will try to be consequential in using small case p, and then for the commutative distribution function, I'll use the uppercase P. And our random variable x can take values on an interval, so it has a minimum value x min, a maximum value x max. Then px times dx, p of x times dx is then the likelihood that the random variable falls somewhere between value x and value x plus dx on that interval. So that's it. So px times dx is a pure number. That is really a probability. By definition, a probability density function is normalized on the domain. So if we defined the domain for x as running from x minus to x max, that means that if we integrate the probability density function from x minus to x max, then the answer has to be 1. That is the normalization. And of course, going back to the example that from the previous slide. So let's say we can write a probability density function for the photon step sizes between interactions. That would mean that indeed px dx, px times dx would be a pure number. That means that px itself, then dx has units meters. So in that case, that means that this probability density function has itself has units per length. So it is a probability per length. And if you then multiply it with the length or with a length segment, then it becomes a pure number again. Then the cumulative distribution function is then is a probability, so it is unitless of the random variable x falling between the lower boundary of the interval, so x minus, and a certain value x. So it is the summation of all the likelihoods up until a value of x. That means that mathematically you can write it as this integral. So the integral adds all the probabilities. So the cumulative distribution function is the integral from x minus to x. There is an I'll be referring you to one of the book chapters later on. There is a little bit of an alternative notation that sometimes pops up there. That is shown here at the bottom. All right. So we can have probability density function for only a single variable, for let's say for x, but we can also define joint probability density function of 2 variables. So in this case, 2 random variables x and y. Here too, x and y can take values on an interval, on their respective intervals, and here too, we'll see that it is normalized. If we now, in analogy to the one variable, if we take this joint probability density function and multiply it with the interval dx dy, then we are calculating the likelihood that the random value x falls between x and x plus dx, and simultaneously that the random variable y falls within y plus di. So it is really a joint probability that both happen at the same time. This one, this one too is normalized. So if we integrate this over the 2 domains, the respective domains, then the answer should be 1 again. And of course, the prime example of a joint probability density function that we saw in this course is the phase function, the joint probability density function of the polar and azimuthal scattering angles, theta and phi, with the intervals theta from 0 to pi and phi from 0 to 2 pi, as you know. If you now look at the units, so theta and phi, d theta and d phi, both have radians as units. So that means that this joint probability density function itself, p of theta and phi, has units per radian squared, or if you like, per star radian. So that's the definition of the star radian. Boom. From this joint probability density function, you can calculate a so-called marginal probability density function. So then basically what you're doing is isolating one of the variables, and you do that by integrating. If you want to have the marginal probability density function of x, you have to integrate over y. So you add all possible values of y together, and vice versa. If you want to have it for y, then you have to integrate over x, and that way add all possible values of x. so I'll give you an example for that as well. So let's take the Rayleigh phase function. It is then is a joint probability density function for the scattering angles, as we said. And this was the formula. You know this, of course, because you've been working with it in the assignment, so you're very familiar with this one. As you can see, it is written as P of theta and phi, but what is a little bit confusing maybe is that it does not have an actual functional dependence on phi. But if you integrate this over sine theta d theta, 0 to pi, and over 0 to 2 pi d phi, then the answer is 1. It is properly normalized. So in order to get the marginal probability density function for theta, that would require integrating over phi, so from 0 to 2 pi over phi, and then you find that the marginal probability density function for theta, p theta, is, as given here, 3/8 times 1 minus cosine squared theta. Likewise, if you want to calculate the marginal probability density function for phi, then you would have to integrate over sine theta d theta from 0 to pi, and that would give you just a constant value 1/2 pi, which is of course consistent with the fact that there is no functional dependence in the original expression. All right, so far so good. Mooi. Yeah, in this case, this is of course good to notice. In this case, the two random variables, the two angles in this case, are independent. So in this case, the joint probability density function can just be written as the product of the two marginals. That is of course very convenient. All right, then the expected value or the mean. To find if you know the probability density function, then you can find it by multiplying the variable with the function itself and then integrating over the domain. This will give you the expected value. Of course, if the PDF has a high value at some x, then that will carry more weight in this calculation than when the probability is low. Okay, some rules for calculations with expectation values. If you multiply x with a constant, then the expectation value just gets multiplied with that constant as well. So that's easy. If you have two random variables, x and y, then the expectation value of their sum is the sum of the expectation values. Also quite useful. And we can generalize this concept to so-called moments, higher order moments. So whereas for the expectation value we have x here multiplied with px, we now have x to some power and some power y, and then multiplied with the PDF. So this is the eth order moment of the PDF that we are calculating here. So if e is 0, then x to the power 0 is 1. So then we just have the normalization property of the PDF again. So the first moment is, or the 0th order moment is 1 unity. Then the first order moment is exactly that expected value that we just looked at. So that is the first order moment, and the second order moment in that case would be the expected value for x squared, the third, etc., etc. All right. So you can use, basically what you can do is use these moments to characterize the PDF. It's more convenient or more conventional maybe to use not use these moments, but use the variance. So the mean and the variance to characterize a PDF. That the variance is defined as the mean squared deviation of the random variable of the distribution around its mean value. This can be convenient because there are some probability density functions that are uniquely described by only the mean and the variance. Okay, do you know an example of such a PDF that is only described, that is completely described by the mean and the variance?
The normal or Gaussian distribution, right?
Yeah, it is the most famous of them all. Yeah, so the normal distribution is actually just has two parameters, a mean and a variance. So if you know that, then you can describe the whole function. Okay, can calculate calculate a little further than that. So if it is the expectation value of the mean square deviation, then we can work out this quadrature equation here. So that becomes the expected value of x squared minus 2x first moment plus the first moment squared. Of course, we had the rule that the expectation value of the sum was equal to the sum of the expectation values. So we can split that here as the expected value of x squared minus 2 times the expected value of x times m1 plus m1 squared. Well, of course, the expected value of x was actually the definition of m1. So here we have first subtracting 2 times the expected value of x squared, and then adding 1 back again. So the bookkeeping results in that the variance can also be written as the expected value of x squared minus the square of the expected value of x. So this is now the variance expressed in terms of the moments of the probability density function. This expression is sometimes useful because if you have in many cases you will have a normal distribution that has 0 mean. So if that happens, then the variance just becomes equal to the expectation value of x squared. So that is sometimes useful. Also for the variance, we have some rules. If you scale the variable x by multiplying with the factor a and setting it off by a factor b, then the variance of that new variable becomes a squared times the variance of x for constants a and b. And also the variance of the sum of the random variables x plus y equals the sum of the variances. Only and only if these variables are uncorrelated. So they are independent random variables. If they are dependent on each other, then you get an extra term in here because of this quadratic nature of this equation. Okay, now finally, one more manipulation that we can do with a probability density function is make a transformation. So let's look at a complex random variable, x plus ey, and let's assume that we have a joint probability density function for x and y, p of x and y. And one such an example is, for example, a phasor in a complex plane. So here we have a vector in a complex plane. Here the real axis, that is x, and the imaginary axis, that is y. And here is in red is a depiction of that phasor, of that vector in the complex plane. So we can describe it as x and y components, but we can also describe it as an amplitude and a phase. So the amplitude being the length of the vector, and the phase being the angle with the real axis. So now let's say we know the joint probability density function for x and y, but what we would like to know is the distributions for the amplitude and the phase. So we need to convert that PDF. So the question is now, how do we transform this p of x and y into a distribution of amplitude and phase? That is done by calculating the so-called Jacobian matrix. So this is a matrix that has the partial derivatives of the variables in the original distribution with respect to the variables in the domain that you want to calculate. So the x dA, the x dv here, and dy dA, and dy dv. And you can make this transformation by calculating the determinant. Is that determinant in English? I'm actually not quite sure. Well, determinant of this Jacobian matrix, and then you can just multiply the old distribution with this factor, with this determinant, and then rewrite the whole distribution in terms of amplitude and phase. So let's take a look at an example for this example. So For this phasor here, we have, of course, that x is amplitude times cosine of this phi, and y is amplitude times the sine of phi. And if you then write these factors in this Jacobian matrix and calculate the determinant, then the result is pretty simple. It is just a factor a. So just this amplitude. So that means that we can apply this. We can write p the PDF of a and phi joint is equal to a factor a times the joint PDF of x and y. Now, let's, for example, let that joint PDF be a normal distribution. So this, what you see here in the top equation is a joint normal distribution with x and y here and some variance over there. And now we're going to calculate. We want to calculate the distributions of amplitude and phase. Well, of course, for this vector, we know that the amplitude is the square root of x squared plus y squared. And the phase is the arctangent of y over x. So using the result from the previous slide, so the joint distribution of a and phi is a times that of x and y. We can immediately write, so this vector a is carried over to here, and x squared plus y squared is a squared. So that enters over here. So this is then basically the joint probability density function for amplitude and phase. As you'll notice immediately that the phase itself does not show up in this expression. So that is a similar situation as what we had with the phase function. This one is interesting, of course, because this is actually the joint probability density function for amplitude and phase of a speckle pattern. So if you, Johannes, talked a little bit about speckle, I think, in the OCT class, if I remember. If you shine a laser pointer on a wall that is a little bit granulated, you will see this. You will see this pattern. If you would take a photograph and not photograph, if you would be able to measure the field, the electric fields in that pattern, then the amplitude of the electric fields would follow this distribution. All right, now this is joint, so we can calculate the marginal distributions. The marginal distribution for amplitude we can find by integrating over phi. Phi, of course, runs from 0 to 2 pi, so if we do that, then the factor 2 pi here drops out. Okay, wow, I forgot about that one. Okay. So now I have a short question for you to see if you can use this as well. So this was for amplitude, for the electric field amplitude. We're more interested in the measurable quantity, which is amplitude. Intensity is amplitude squared. So the question is, can you now convert this this marginal distribution for amplitude into a distribution for intensity? And of course, the hint is already in the line there.
Yeah, so I found something.
Right.
Of course, the hint's already given, so we first want to calculate the Jacobian in order to find the factor that relates the two functions. So we have the intensity equals the amplitude squared. If we rewrite that, we find that the amplitude equals the square root of the intensity. The derivative of the amplitude in terms of the intensity is then
Sharon, is this your background or?
No, I don't think it's
yes,
me.
unfortunately it is.
Yeah, so I've posted my result. I think what I did is I computed the Jacobian, so the A over the I got that was 1/2 I to the power minus 1/2.
Mm-hmm.
I plugged this into the equation for PA and substituted y for a squared.
Yeah.
And then you find that the amplitude in front of the exponential drops out due to the Jacobian and the substitution. And in the exponential, you're left with a minus I.
Yeah. Yeah. So this is then the result that I got. Yeah. So what basically happened now is that the shape of the distribution has changed. So this the distribution of PA. This is a so-called Rayleigh distribution, which has both this linear term and this exponential decay term. But the intensity is purely exponentially distributed. So here the prefactor here, but other than that, we just have an exponential decay. Okay, then we can actually was I intended to make this a question, but well, apparently that backfired. So we can let's do it this way then. We can calculate the first moment of the intensity now, the average intensity, by multiplying E with its distribution and then integrating over the domain. So intensity here can take values between 0 and infinity. It is a measurable quantity, so there is not such a thing as a negative intensity, but other than that, it can theoretically go from 0 to infinity. So we can perform this integration, make some substitution, variable substitutions here, and then in the end get the result here. That's the average intensity by this. Given by this PDF is given by 2 times sigma squared, and not coincidentally, that is the same 2 sigma squared that is also present here. So we can make then that substitution. There we go, and get this basically this final expression for the PDF of the intensity and the speckle pattern. So it is again a purely exponential distribution, and it only has one parameter, namely the mean of its mean, the mean intensity. All right. I guess a few minutes early, but I think this is the best moment to have a short break, because otherwise I'm starting all over on a new subject. So let's take a 15-minute break. And then we'll start again at, so that is at 14:25. Okie doke.
All right, see you then.
Yep.